Welcome to this explainer. Look, if you've ever stared at abstract lines of Verilog code and wondered, is this actually going to behave the way I want it to in the real world? Well, you're in exactly the right place. Today, we're focusing entirely on how to use Questa simulation. We're going to take a completely blank screen and transform it into a powerful testing ground for your code using the Questa Altera FPGA simulator. We are officially taking the guesswork out of hardware design.
Here's a quick look at our roadmap for today. We'll start by meeting your simulation tool, setting up the project, and preparing the waveforms. Then we'll run your first simulation, look at modifying and restarting, and wrap it all up by mastering edit mode.
All right, Section 1, meet your simulation tool, otherwise known as the sandbox for your code.
So the absolutely crucial thing to understand right off the bat is that the Questa Altera simulator, specifically the free starter edition we're looking at today, is a dedicated standalone sandbox. Before we start clicking buttons and writing logic, we need to establish that this is an environment completely separate from your physical hardware. This is where your abstract Verilog code literally has to prove its worth. It does this by taking the exact inputs you inject into it and generating a graphical waveform of the outputs. It's basically a virtual stress test for your logic gates.
Moving right along to Section 2, setting up the project, or building the foundation.
To get our 4-bit adder project ready to go, we're going to follow a simple procedural build. Treat this exactly like a recipe. You're gathering your digital ingredients and mixing them together. We'll start in your main design software, jump over to QuestaSim, pull in your existing Verilog file, in this specific case that's adder.v, and finally, compile the whole thing together so the software actually understands your logic.
You know, your very first micro-victory actually happens over in the Quartus Prime software. Before you even open Questa, you have to go into your EDA tool settings in Quartus and explicitly tell it, hey, use QuestaSim for simulation and set the format to Verilog HDL. This is the crucial handshake between your design environment and your simulation environment.
Once that handshake is locked in, you launch the standalone Questa software. You'll go to File, then New, then Project, and you'll see this prompt pop up. Here, you name your project, something simple like Adder Sim. But the vital step here is mapping your project location exactly to the directory where your Quartus project lives. This is absolutely necessary because it ensures your simulation has direct access to the Verilog files you just wrote. After that, you simply add your existing adder.v file and hit Compile All.
Section 3, preparing the waveforms and injecting inputs.
Okay, now that our workspace is compiled and error-free, it is time for the fun part, setting up the actual simulation environment. You'll go to Simulate, Start Simulation, and select your Addern file from your work directory. Boom! A blank wave window appears. Now, before you do anything else, actually, scratch that. The very first thing you need to do is right-click in that wave window and set your zoom range. We're setting it from 0 to 800 nanoseconds. Why? Because you need to frame the upcoming action. If you don't set this, your results might be zoomed in so tightly or zoomed out so far that you totally miss the exact moment your logic reacts.
Next up, we need to feed this 4-bit adder some math. Over in your Objects window, you'll right-click your inputs to modify them. We're applying constant waves here. We'll set our carry in to 0. Then we'll set input x to the binary value 1011. And input y to 1001. Once your inputs are primed for that 800 nanosecond chunk of time, highlight your expected outputs, which are sum, carryout, and overflow, and drag them straight into the wave window. And just like that, your test bed is fully loaded.
Section 4, running your first simulation. This is where the math becomes visuals.
Here is where things get genuinely exciting, because we're about to turn those static binary inputs into dynamic visual data. But right before we hit run, let's take a quick look at the logic we're actually testing. This brilliantly illustrates the mathematical brain inside our code. It's the Boolean equation governing the overflow output of our 4-bit adder. Remember, our simulation isn't just drawing pretty pictures. It's calculating this exact formula, bit by bit, to tell us if adding our two numbers exceeds the capacity of our 4-bit system.
All right, with that logic in mind, head up to your toolbar. Double-check that the simulation duration box says 800 ns, matching the zoom range we just set. Then, click this exact run icon right here. It looks kind of like a little piece of paper with a downward arrow. Hitting this executes the whole simulation. And boom, your first major victory.
Instantly, the wave window populates. If your Verilog code is spot on, you should see exactly these results. Your sum is 0104, your carryout is 1, and your overflow is 1. The software perfectly calculated that 1011 plus 1001 yields this specific result. Now, pro tip, before you do anything else, go to File, Save Format, and save this layout as wave.do. Do this so you don't lose your specific window arrangement and have to manually drag and drop your signals every single time you open the project.
Section 5. Modifying and restarting. Iteration is key, guys.
Look, hardware design is literally never a one-and-done deal. You test, you tweak, you test again. So let's test a brand new scenario without blowing up our whole project setup. We're going to inject new inputs by right-clicking our X and Y signals right there in the wave window. Go to Edit, Wave Editor, and let's modify the waveform. We'll change X to 0110 and Y to 1100 for the exact same time duration.
Now pay super close attention here. See that restart icon right next to the time duration box? Before you run your new math, you absolutely must click this restart button. It clears the simulation timeline back to 0, but it magically keeps all your formatting and those new input rules perfectly intact. So click restart, hit OK, and then hit that run icon one more time.
Almost immediately, your waveforms will update to reflect the new mathematical reality. With those new inputs, your timeline will now show a sum of 0010, a carry out of 1, but check this out, this time an overflow of 0. You've just successfully iterated your test, proving that your code flawlessly handles multiple, totally different scenarios.
And finally, Section 6, Mastering Edit Mode for Advanced Waveform Tweaks.
Using menus to manually type in binary values is totally fine. But let's explore a way faster, far more visual way to manipulate your simulation data directly on the timeline itself. Keep an eye on your toolbar for this specific button, the Edit Mode icon. When you click this, the software shifts gears. Instead of just letting you view the waves, it lets you treat them like physical objects. You can literally click, drag, and highlight a specific chunk of time right there on your input wave.
Once you've used your mouse to highlight a specific section, let's say from 200 to 400 nanoseconds on an input, you just click this invert icon. Instantly, whatever was a binary 1 becomes a 0, and whatever was a 0 becomes a 1, just for that selected time range. It's incredibly satisfying, and it dramatically speeds up how fast you can test those weird edge cases.
But here is one absolute must-remember pro tip. Always click the standard cursor, the select mode icon, when you're done making these visual changes. This safely exits edit mode. If you forget, you're going to accidentally invert a wave when you're just trying to pan across your timeline to view your results. Trust me, you don't want to do that.
And that brings us to the ultimate takeaway. By mastering the Quest to Ultra simulator, you aren't just drawing pretty green lines on a screen. You are radically de-risking your entire engineering process. You're stress testing your logic, you're sniffing out those overflow errors, and you're fixing your broken math in a completely safe, totally free sandbox way before you ever touch a real expensive circuit board. So you really have to ask yourself, how much time, money, and sheer frustration did this simulation just save you? Keep that in mind the next time you compile. Thanks for joining me on this explainer, and happy simulating!